So lesson 7.2 is exponential growth, and the big idea says that growth at a constant percentage rate can be described by an expression of the form b times g raised to the x, where g is greater than 1, and the variable is the exponent. Okay, so that's a very mathematical definition. So we're going to look at exponential growth as opposed to constant growth, and very much like we were looking at compound interest in lesson 7.1, where things grow faster over time because it's growing by a percent every single year. So if there's a bigger amount of money every single year in your account because it's grown from the previous year, now the percentage of that is going to be even bigger. So the amount of growth every year is actually larger, even though it's the same percentage. So we're going to look at things that aren't necessarily tied to money, but also kind of follow the same rules as exponential growth. And you'll see the similarities between this formula and the compound interest formula. Okay, so exponential growth comes in this formula. And that's what we were looking at there. So it's when things grow exponentially. And we need to define what all of this means. So y is going to represent your total amount. B is the beginning amount. And so if we're going back to interest, that's like your principal, what you started with. G is your growth factor. That's like the percentage that it's growing. And X is your time, basically. We had T there in our compound interest formula. So X is the number of time periods. Now, when we deal with exponential growth, G always has to be greater than 1, so more than one time period. We're not looking at less than 1. So if this number was less than 1, if you think about it like a decimal, okay, when you multiply by a decimal, things get smaller, and we're talking about growth. So this needs to be a number that's greater than 1, so that when we multiply by it, it's actually increasing and growing. That's what we're specifically talking about. So your growth factor here, that's the number that's being raised to an exponent, which means it's the number that's being repeatedly multiplied. The equation, we've already got it. It's right here. And it's also very important to understand the zero exponent property. Anything raised to the 0 power so for instance, x raised to the 0, or even if it's a number, 5 raised to the 0, we talked about this in middle school, is 1. And you can try it in your calculator. Raise anything you want, 5 raised to the 0, and you get 1. And we talked about that before, why that is, but right now we just need to know that it is. So anything raised to the 0 power is 1. All right, so let's jump right in. Let's apply this. If we slide down to example number 1, we're going to calculate how much growth has happened over 5 years, 10 years, and 20 years. So 26 rabbits are introduced to an area. If the rabbit population doubles every year, how many rabbits will there be in 5 years, 10 years, so on and so forth? So if you think about it, if there's 26 rabbits and then it doubles, 26 times 2, that's 52. So it's gone up by 26. We're now at 52. But now that 52 is going to double. So that's 104. Right? So let's actually write this out. So we're starting with 26. After 1 year, you're going to have 52. After 2 years, it's going to double. You're going to have 104. After 3 years, you're going to have 208. After 4 years, double that. You're going to have 416. So after 5 years, it's going to double again, and you're going to have 832. So you could do it that long way, of course, but we want to try and use this formula so we can get to this answer a lot faster. So 5 years represents your time. That's going to be your x in this equation. So y equals b times g raised to the x. We got to plug everything in the right spot. So y is kind of like your answer, so we can just leave that. B is what you start with. It's like your principal when you're talking about money. So 26. We already said x is 5, so we're just worried about g. G is your growth factor. What is it changing by? Well, it's doubling every single year. So doubling would be timesing by 2, right? Every single year you're timesing by 2. So if it was just 1 year, you're timesing by 2 to the first. 1 year, just times 2. But now we're actually, if you look at it, we're not timesing by, if we're going from 26 to 104, that's actually times 4 because it's 2 years, that's 2 to the second. So the x value up here is the number of years. So that's 5. And if we did 2 raised to the 5th, that's 32. Now you don't have to actually write this out, but 2 raised to the 5th is 32, and 32 times 26 is going to get you that 832. So your final answer here is 832 rabbits. Now for one that's small, like 5 years, you could just keep doubling it and get to the answer. But obviously, the more years we add on, the less efficient this model is, and the better that formula works. So how about 10 years? So the total amount of rabbits, we started with 26. They're doubling every year, so that's 2. The amount of time is 10. So 2 raised to the 10th times 26. Remember your order of operations. If you were plugging this into a calculator and you were going to do it one step at a time, exponents first. So 2 raised to the 10th, get that answer, then multiply by 26. And that comes out to 26,624. So you went all the way from 26 rabbits. And if they double every single year, you now have 26,624 rabbits after 10 years. So you can see this is not constant growth where you just add 2 rabbits every year. So you had 2, then you have 4, then you have 6, then you have 8. This is exponential growth, things growing exponentially. Okay, much faster, obviously. And how about after 20 years? So same equation, starting with 26. Growth factor is 2 because they're doubling every single year. And after 20 years, 27,262,976 rabbits. So you can see exponential growth is going to have a much faster and higher rate of an increase than a constant rate like a line. So this is not going to be a line on a graph. If after 20 years it's all the way up to this, you think about it, this is going to quickly curve up. And we will look at graphs of these in just a couple minutes. So let's try one more example. If you flip it over, you have a plant and it sprouts to 2 centimeters tall. Every week after when it's measured, the plant has grown 20%. All right, so the question's a little different because it's given us a percent. Instead of saying that it doubled, it's giving us a percent. It's 20% bigger. So that's not doubling. Doubling would be 100% bigger. It was 2 centimeters tall, and if it doubled, it'd be 4 centimeters tall. But it's growing by 20%. So if we take our 2 centimeters, and we find 20% of it times 0.2, that means it's growing by 0.4. 20% of 2 is 0.4. So if it started as 2, after 1 week, it's 20% bigger, meaning 0.4 has been added on. So it's at 2.4. But now it's not going up by 0.4 every single time. Now it's going to grow 20% bigger than that. So you're going to take your 2.4, 20% of that. So times it by 0.2 is 0.48. And so it's going to grow now instead of not just by 0.4, but by 0.48. So that's going to be 2.88. And then it's 20% of that number. Okay, and so 20% of each one of these bigger numbers is a larger amount than 20% of the original. And so it starts growing faster and faster and faster. So let's go ahead and use our formula. This would be x equals 1. That's the amount of time. So if we're plugging into our equation, y equals b times g raised to the x. B is your starting point, so 2. Now your growth factor is not going to be 0.2 because remember that number needs to be greater than 1 because if you multiply by 0.2, this gets smaller. Now we did that and then added it on. So we need to think about what is it becoming? So from 2 to 2.4, it's 20% bigger. It's the original plus 20%. So the original is 100%, and we've added 20% to it. So this number actually represents 120% of the original. It increased by 20%. So now it's 120% of what it used to be. So we need to express this number here, the growth factor, as a decimal that represents 120%. If you just say 20%, you're making it smaller. It's now shrinking down to 20% of what it used to be. We want it to grow by 20%. So that means it becomes 120%, which is 1.2. If you want to put 1.20, that's fine. And you're raising it to the first power. Let's use a different color here. And so really this is just to the first is 1.20. You're timesing it by 2. And that's going to be the 2.4 that we had right there. Now, how about after 5 weeks? If we continue this out, this gets very, very tedious because you have to keep multiplying by 0.2 or 1.2 and going from there. So let's use the formula now to solve this. So y equals b times g raised to the x. So b is still what it started as, 2. Your growth factor, it's still 20% bigger, so that's 120% of whatever it used to be. And now we're raising that to the 5th power. The calculator will do all the work. Once you know how to set it up, pretty simple to get to your answer. Comes out to this. This is centimeters. And how about after t weeks? So if they put a variable there, they're not actually asking you to calculate something. They're just asking you to set it up and put the variable there. So y equals b times g raised to the x. So we've got 2 times. G is still 1.20. But now it's raised to the number of weeks. So we're just going to put t there. And you can't multiply this and then put the exponent on it because order of operations says I'd have to raise it first. So there's nothing else I can do here. I'm just going to leave it like this. All right, so let's see what this looks like on a graph real quick. Starting with this equation, y equals 2 raised to the x. Let's make a table, so a quick xy table. And then we'll put it on the graph. So starting with these values, so x is 0, 1, 2, 3, and 4, plugging them in. So if x is 0, well, anything raised to the 0 is just 1. Well, what if x is 1? Plugging 1 in for x. 2 to the first is 2. 2 to the second is 4. 2 raised to the third, 2 times 2 times 2, that's 8. And 2 raised to the fourth, 2 times 2 times 2 times 2 is 16. So you can see that the growth factor is 2. Y is doubling every single time from 1 to 2 to 4 to 8 to 16. It's not increasing by 2 every time. It's being multiplied by 2 every single time. It's doubling. So what does this look like on a graph? So our x values, we've got 0. We want to have 1, 2, 3, 4. You could spread them out if you wanted to. And then our y's need to go all the way up to 16. Okay, that's not really going to fit on this, so let's count by 2's. 2, 4, 6, 8, 10, 12, 14. We need to go all the way up to 16. Okay, so if we're at 0, we know that y is 1. If we're at 1, oops, see, I put that on the wrong line there. I put that at 2, so it needs to be 0, 1. So cross that out. Right here, 1 is halfway through that line. So when I get to 1, now it's at 2, which is right here. So that looks like a straight line. Any 2 points are going to form a straight line. But let's see what happens. We get to 2, and now it's up to 4. Kind of looks straight. Starting to look a little goofy. And now from 3, it's all the way up to 8. 4, it's all the way up to 16. The next one will be 32 way up here. And so what you start to see is this exponential growth is going to form a curve that just keeps getting bigger, faster and faster and faster and faster. All right, sliding down to the last piece. Number 4, I want you to start being careful. Okay, that x value, where it represents time, is not always 1 year, 2 years, 3 years, 4 years. It can represent blocks of years, and that's what we're going to see here. So from 1930 to 2000, California's population could be modeled with this equation. And so we're going to talk about what all these numbers represent. Y is the population in millions. And so whatever number we get for Y, it's that million. If we got 10, it's 10 million. And X is the number of decades. So not years, decades. And decades is blocks of 10 years. So if it's 10 years later, that's 1 decade. So we wouldn't put in 10 for 10 years later, we would put in 1. We'll talk about that in a second. So what does 5.68 represent? So that's sitting there in that first spot, the B spot, which is whatever you're starting with. So that means that's the population you started with. And in this specific situation, we started in 1930. So that's the population of California in 1930. That's what you're starting with. 1.29 is your growth factor. So it's growth of, now it's always going to have that 1 there unless it's growing even bigger than 200% or 300%. So that's 129%. So it's growth of 29% per, not per year, but per decade. Okay, so it's growing by 29%. It's getting 29% bigger. It's going to be 129% of what it was every single year. So now let's actually use this. What will the population of California be in 1940? So the mistake here is to say, well, it's been 10 years. I'm going to plug 10 in for X. But X represents the number of decades, not the number of years. So instead of raising this to the 10th, 10 years equals 1 decade. And so since X represents your decades, we're plugging in just a 1. So not 10, 1. It's been 10 years. That's 1 decade. X represents the decade, so we're plugging in a 1. And so when you multiply this out, anything raised to the first, that's just going to be 1.29. Multiplying, we're going to get 7.3272. Now, don't say people. It's not 7.3 people. It's million people. Because they told you Y is the population in millions. So 7.3 million people. All right, last and not least, what will the population be in the year 2000? So we're going from 1930 to 2000. That's 70 years. So that's 7 decades. So when we go to plug in for X, we're not plugging in 70. X doesn't represent the years, it's the decades. So Y equals starting point of 5.68 million, increasing by 29%, so 129% of it, and for now 7 decades. So you would raise this to the 7th, and you would multiply, and it comes out to 33 point, and then it's a long decimal. If it says to round, you can round it, but if it doesn't, then let's write it all the way out. And again, this is million people. So you can see constant growth and exponential growth, much different. Constant growth consistently goes up by the same amount every single year, where this is going up by the same percentage. Exponential growth, much faster.